Welcome to our live webinar on Sparkplug B and OPC over MQTT for Industry 4.0, sponsored by Fraunhofer and Automation.com, a subsidiary of International Society of Automation. I am Jack Smith, Senior Contributing Editor of Automation.com, and I will be your host. Interoperability and scalability are key requirements for the implementation of Industry 4.0 applications. Loosely coupled systems using standardized interfaces and information models are needed to decrease considerable manual reconfiguration effort. Publish-subscribe communication is well suited for the implementation of loosely coupled systems that can be implemented using MQTT. Specifications like Sparkplug B and standard OPC use MQTT as a transport protocol and add necessary missing features. Today, you'll learn how modern loosely coupled systems can enable application interoperability and scalability. You'll learn how Sparkplug B and standard OPC use MQTT as a transport protocol to enable Industry 4.0 applications. And you'll learn how Sparkplug and OPC over MQTT compare for enabling plug and work and condition monitoring applications. Okay, we'd like this to be an interactive session. So before we get started, please take a moment to acquaint yourself with the features of this GoToWebinar technology. On the right side of your screen, you will see a questions tab. Click the text box, enter a question, and click send at any time. All of our questions will be seen only by me and our speaker. Once the main presentation is over, I will ask our speaker to respond to as many questions as possible while keeping the overall presentation time to 1 hour. This presentation, including Q&A session at the end, is being recorded, and afterward, you will be emailed a link for viewing it later. This presentation will include poll questions. Your anonymous answers will be collected and answers will be presented immediately. Also, within the tabbed menu, you will see a tab specifically for handouts. If there are any items available to download, you will find them there. Okay, let's hear some background about our speaker. Florian Pethig has been Deputy Head of Machine Intelligence at Fraunhofer for more than 13 years, and he is also Group Manager of Big Data Platforms at Fraunhofer. Florian studied electrical engineering and information technology at the Technical University of East Westphalia-Lippe in Germany. He has been working on interoperability and data management in the context of Industry 4.0 and digital twins for 13 years. He has been managing the research group on big data platforms for Industry 4.0 since 2017 and is Deputy Head of Department for Machine Intelligence and has been so since 2023. At Fraunhofer IOSB-INA, and his research group work in projects, especially with industrial companies where they help to implement modern data infrastructures and IoT platforms to increase resilience and flexibility of production systems. I know we're all looking forward to hearing what Florian has to say today, so I'll turn the microphone over to him. Florian?
Hello, everybody, and thanks, Jack, for the nice introduction. Nothing to add there, so I'd say let's get to business. So my talk today will be heavily based on the publications we can see on the slide here. The one at the top has been published on automation.com end of last year, and you can access it via the QR code on this slide. And you can also find this publication and also the second one in the handout of today's webinar. The second publication, the Industry 4.0 Communication Guideline, we wrote already in 2017 together with the German VDMA, which is the Mechanical Engineering Industry Association, representing 3,600 German and European mechanical and plant engineering companies. Let's look at the agenda real quickly. So let me just shortly introduce my employer to you, since I think not everybody over there knows what the Fraunhofer Society is. And let me also take 1 minute to present our region in Germany to you, where a lot of companies stem from that you might know. Then we will look at Industry 4.0 as we see it here, especially in Europe, and application scenarios and their requirements from Industry 4.0. We will then look at solutions that are frequently used to implement these Industry 4.0 application scenarios like MQTT, Sparkplug B, and I will say Sparkplug from now on only, and OPC UA over MQTT. We will analyze these solutions in a requirements analysis according to the requirements from the application scenarios introduced before. Then I will conclude my talk, and hopefully we have a lot of time left for a fruitful discussion. So let's get started. The Fraunhofer Registered Society for the Advancement of Applied Research is a German research organization with 76 institutes spread throughout Germany, each focusing on different fields of research. We have some 30,800 employees, mainly scientists and engineers, and we work on an annual research budget of about 3 billion euros. And thus we are the biggest organization for applied research and development services in Europe. So the most interesting point on this slide here is at the bottom right of this corner. So we are a registered society, basically not a company. We get some base funding from government, but the main point here is that 70% of our budget stems from industrial contracts. So mainly we do research for and together with industrial companies. We are located in the middle of Germany between Hamburg, Hanover, and Dortmund in a region called Ostwestfalen-Lippe, East Westphalia-Lippe, and we are honored to be funded by the German government as the only technology leading edge cluster for Industry 4.0 already since 2012. And since 2012, we already worked on a project's budget of over 300 million euros in our leading edge cluster. And as I said before, you might know some of the companies that have their headquarters here in our region, presented on this slide. Zooming into this region, I am from Lemgo. You can see a picture of the old Hanseatic town on the right, and on the left you can see the inside of our Smart Factory OWL, which is our test and demonstration platform and smart factory, of course, where we evaluate our research results in a real production environment. So we have some demonstrators from research projects here, but we also have a real production producing plastics, producing coffee cups to be exact, that is running in a real production scenario and where we gather real production data and which we heavily use to evaluate our data infrastructure, for instance. Here, zooming out, an outside view of our institute in the front, right, connected to the Smart Factory OWL that you can also see from the outside here on this slide. Last slide for the intro, I promise. Here are our research and application domains, and we say we work across the whole Internet of Things technology stack, beginning on the left with smart sensor systems, where we acquire physical signals and communicate these data with industrial communication and IoT technologies. Then we manage this data in big data platforms, hopefully do intelligent stuff with machine learning and symbolic methods and optimization. The human being, of course, always has to interact with the data still. So we also work on systems for all these data that we are gathering, and we consider cybersecurity across this complete Internet of Things technology stack. We apply this stack in our two application domains. Today, of course, we focus on industry and our Smart Factory OWL as a living lab for this application domain. But just for completeness, let me say that we are also active in the smart city sector, where we are proud that we can also use our hometown of Lemgo as a real living lab, where we, for instance, also install a lot of sensors. And the newest addition here in our group structure is a group focusing on data-driven business, where we work on business models. So until now, we worked a lot on technology, and now we also, of course, get more and more questions from the companies. Okay, how can we earn money with all this data? Okay, then we already come to Industry 4.0 and how we see it here in Europe, in Germany especially. And here, Industry 4.0 is heavily connected to a organization called Platform Industry 4.0. Since 2013, this Platform Industry 4.0 is shaping the digital transformation as a manufacturing network here in Germany, and it builds on well-established associations like the VDMA mentioned before, but also the ZWEI, which is the Germany's Electro and Digital Industry Association, accounting for as well 6,000 member companies. And if we think about Industry 4.0, it's all about the 2030 vision that we see here on this slide, where we want to gain autonomy, work on sustainability, for instance, for climate change mitigation and the circular economy. And it's also a focus for today, especially interoperability, where we think that standards and integrating decentralized systems is of utmost importance. So key aspects of Industry 4.0 for us are to increase the flexibility of production systems to rapidly adapt to change. For instance, in scenarios like plug and work, what that is, we will see in a minute. And as well, condition monitoring is a very important application scenario in the context of Industry 4.0. It's a real basic application scenario, of course, but it's also a base requirement for resilience by preventing failure in our production systems. And what we see is that to implement these application scenarios, we need to distribute our functions across the network. All participants across all hierarchy levels of our automation pyramid that we had in the past have to communicate with each other. So if you remember the automation pyramid, there we have the hierarchy levels, and only hierarchy levels directly connected to each other communicate with each other. And here in this Industry 4.0 architecture, we want basically all participants to be able to communicate with each other, just like you see it on the figure on the right. And very important, we want to create added value by exchanging information between value chain partners. And what we see is that for this, we need a dynamic, loosely coupled industrial Internet of Things as a base architecture to implement these key aspects. So what are the challenges to implement this? I also like this slide from the Platform Industry 4.0 a lot, where we ask what's new really. So we have a lot of things already today, like the cloud and automation devices with Ethernet ports and internet access and so on. But the main new ingredients, also according to the Platform Industry 4.0, is that we move out of our company intranet to the internet with our valuable information, and to exchange this valuable information across value chain, across the life cycle of components and assets, we need standards. So standardization is key. We need neutral and common standards for communication services and semantics across companies and sectors. And the hypothesis is that a large number of new applications and business models will emerge. So we can already derive general requirements for Industry 4.0 from this slide here, which is international standardization. And of course, standard is only worth if it's being adopted, hopefully by major companies. And you also want to comply to the standard if you implement a product. And of course, you want to also have a certification of your product to assure reliable products that implement this standard. So let's look at the first application scenario for today, which is plug and work. And there our goal is to increase the flexibility and changeability of production systems through automatic configuration. So you can think of it a little bit like the USB, right, which we know from the office, from our laptops, where you plug in, for instance, a printer and it's automatically configured. Some magic is happening behind the scenes, drivers are installed and so on. And of course, automation is much more complex. That's why it's not being implemented today, but this is the goal here, right? To have a similar flexibility and changeability of our production systems, to integrate new components, modify components, and also extract components if we want to disable a certain functionality. And there are certain challenges, when we want to implement plug and work, because if we look at the picture on the right, we have the heterogeneous environment. Of course, everybody knows that different communication protocols and especially different information models between all these different solutions here in this picture. And there's a lot of high manual effort involved for reconfiguring such hard-coded and proprietary systems. And that is, of course, time-consuming and error-prone. So what we basically need for the implementation of plug and work are the requirements, which we see here already on the slide. We need uniform interfaces, not 3 or 30 different solutions, 30 different interfaces. We need machine interpretable and uniquely identifiable capability descriptions of our stations here in this example. And we need modular information and control structures that are adaptable. That's plug and work. In the second scenario, condition monitoring, there, of course, the goal is to monitor the condition of our equipment, can be components, can be whole plants as well. And we want to do that via suitable data variables, of course, for instance, vibration, temperature, and we do this particularly for anomaly detection. And there, today, the challenge is that especially the data collection suffers from challenges regarding the variety and quantity of the heterogeneous data in the field. Again, the different interfaces and information models that we see, and additionally, we have a challenge that we establish point-to-point connections, mainly via client-server communication today. But I guess you already know about this challenge since you are here in the webinar today. So let's derive some requirements from this application scenario as well. And these are also a uniform interface for our data acquisition, a standardized semantic information model to being able to automatically map data variables from source to sink systems. Then we need a scalable solution. And as we often move out into the internet, into the cloud with our condition monitoring systems of whole plants, we of course also have to consider cybersecurity. And sometimes we install additional small sensors that rely on batteries, that rely on mobile networks. So low bandwidth is also one requirement, condition monitoring. Okay, so let's put it all together. Let's put the requirements together here from our application scenarios. We started with the general requirements and we can directly overtake these. We want to have an international standard that is adopted and that we can certify our compliance to. And then we have these two application scenarios, plug and work and condition monitoring, and they both have the requirement uniform interfaces. So we merge this requirement to an overall requirement R1 here. Then we have machine interpretable capability descriptions for plug and work and modular information control structures for plug and work. And we have standardized semantic information models. And here the point is that these capability descriptions and modular information and control structures can also be contained in standardized or are contained in standardized semantic information models. So we merge these requirements to our requirement R2 here on the right. Then we have the additional requirements from our condition monitoring scenario, which is scalability, low bandwidth, and cybersecurity. Okay, then let's already look at solutions that are used to implement these application scenarios. And a solution that is achieving increasing attention for IIoT use cases is, of course, MQTT. MQTT is the de facto standard specified by the Organization for the Advancement of Structured Information Standards, and version 3.1.1 of MQTT is also standardized as an IEC standard. The latest version 5 adds features that evolve around handling topics mainly. And the reasons why MQTT is so in favor today are its simplicity, it's said, the lightweight and bandwidth efficient communication with a minimal overhead, and that it's data agnostic. And here I would already like to involve all of you. So I would like to ask you, what do you think? Is this MQTT being data agnostic actually a pro or a con? I don't know, Matt, if you want to start the poll right away. I guess it's running, so you can now click the options, and then we'll also see the results shortly. And I would just continue speaking here. Okay, you see the poll, I guess, and you will see the slide after the poll is finished. No, it should be finished. And we see that, oh, that's interesting. 83% said that MQTT being data agnostic is actually a pro. Okay, let's see what you think after our talk today. So what I want to mention is, talking about MQTT or talking about Sparkplug or talking about OPC OA, let's keep the OSI model, communication model, the layered model you can see on the right of the slide always in mind. So MQTT sits on top of the TCP IP stack, can also be tunneled through web sockets, of course, but basically it's a TCP IP based client server protocol. Yeah, that's specified here. And why is it so achieving increasing intention for IIoT use cases? Let's look at this for a minute. So classic automation, of course, requires deterministic and robust real-time communication, where we see real-time systems for good reasons like Profinet, Ethernet IP, and so on, especially between PLCs, components that should be controlled, and so on. And then we moved in the past and also still today from the PLC to different systems like a SCADA system, like a historian, like an analytics system. And we stick to the classic connection-oriented point-to-point approach. So what we do here is we establish connections from this PLC to all of these different systems. And I think you can already guess where this ends up. So we have, for instance, also here robot stations speaking some legacy protocol, where you even need some gateway to translate it and to connect it to the systems on the right of the slide. And it gets even more complex. You have a lot of connections. That's the basic point here. Of course, you have point-to-point architecture, and you have manual data mappings as well. So if you want to acquire variables, for instance, from the injection molding machine, you select manually which variables you want to acquire to which of these systems and how to interpret them and so on. So a lot of manual effort involved, and also this architecture, network architecture, just does not scale. And it gets even worse. So these systems more and more are in the cloud, and there we of course have the unreliable internet, and connections suffer unreliable networks. So connections might not even be possible. There are firewall restrictions. And this is, of course, also a big challenge. So where we are moving here and why MQTT is getting this more and more important today is that we move to a publish, subscribe, pub/sub architecture for scalable IIoT. And there we have a message-oriented infrastructure. And you see that this architecture diagram already looks much nicer. Yeah, we have connections from our different systems, the gateways and the PLC, to this message-oriented infrastructure, where they publish, for instance, their temperature value once, and this message-oriented infrastructure then takes care of getting this data to all systems that are interested in it. It can be as many systems as you want, but the injection molding machine, to stick to this example, only publishes this value once. So you can think of it like a TV station, for instance, broadcasting to as many receivers as there are. So, and this is of course a big advantage from the architecture point of view. And what MQTT then does is it defines this protocol that we saw before between an MQTT server, which is a message broker, and different MQTT clients that connect to this message broker to publish their data and to subscribe to different data. And these data are published to so-called topics in our message broker. And there we can also already come to some challenges and think about what MQTT does not solve. So basically MQTT is just a transport protocol. So it sits on top of a reliable transport protocol, like for instance TCP, and defines this publish subscribe mechanism. And we said data agnostic is a pro. The payload can be anything. It's data agnostic. But does that really help? On the other end, so the SCADA client, of course, subscribes to this topic and has to understand this payload. So you have to implement the structures, data structures in the SCADA client that the robot station publishes to understand it manually. That's the main point. So for industrial use cases, this often also does not scale. It's another aspect of scalability. And also these topics are not specified in MQTT. So if you look at the orange topic here, it's just a random topic, and the SCADA client has to know which topic to subscribe to. And this is not specified. So the messages that the SCADA client is looking for can be anywhere. And also there's no way to know if devices are online or offline, or if messages have been received. So in this example, the SCADA client does not know if the robot station is currently online and publishing data. And the security in MQTT relies on the transport layer below, so transport layer security, which is TLS. And if we look or think about our general requirement from the beginning, I would say that Industry 4.0 requires standards, and also for MQTT payloads and topics. And this is also exactly what the following technologies address. For instance, Sparkplug over MQTT, as we will see in a minute. Sparkplug B has been released in 2016 and is aiming at increasing exactly this interoperability of MQTT-based solutions in the IoT. Since 2019, it's an open source specification that's hosted at the Eclipse Foundation, and the Eclipse working group is currently driven by 14 main members. Since late last year, Sparkplug B is also standardized as an IEC international standard. And what Sparkplug does, it is, defines the structure and state of data within MQTT messages. So exactly this topic namespace that we just talked about is specified. The payload definition is specified, so you're not that data agnostic anymore. You have a state management, so you know if devices are online or offline. And there are some basic principles, like that you only send values if they change, which is called report by exception, that you have this continuous session awareness, and this birth and death certificates that we will also look at a minute. And on the right, again, you can see the OSI network, the layered network model, and there you see that the Sparkplug B communication model sits on top of a message mapping called protobuf. What that is, we will also see in a minute, and that is transported then via MQTT and the TCP/IP stack that we already saw before. The Sparkplug architecture looks like this. So we already saw this basic PubSub-based IoT architecture. And here we also have our MQTT broker, where we connect different systems like Historian and Analytics on the left. And then we connect devices via so-called edge nodes in Sparkplug to this message broker. And these nodes publish data for the devices that are connected to the nodes again. So like a gateway, you can think about it like this. And the architecture is centered, that's the main point here, for Sparkplug around a so-called primary application. So Sparkplug focuses on a SCADA solution sector. So here in this example, that would be then a SCADA application. And this also comes again with some challenges. So here it's all about publishing data and subscribing to data from this primary application. So we pack up all the data from our edge nodes, send it to the broker, and the primary application subscribes to all of this data of our edge nodes, and the primary application can of course also publish, for instance, commands to edge nodes and so on. But one challenge is, for instance, that if the primary application quits, then everybody quits publishing data. So the edge nodes quit publishing data, and for instance, the historian and the analytics system also don't receive any data anymore. And yeah, as I said, the edge nodes pack up everything, all the data that has to be published, and it's published as a whole. So you cannot subscribe to just certain tags of a device that's connected to such an edge node. So let's look at the topic namespace that Sparkplug-B defines just real quickly. It looks like this. We have a namespace, which is always, currently in the current version, SPB version 1.0. Then we have a group ID to group our nodes logically. We have different message types, for instance, birth and death certificates. What that is, we will see on the next slide. We have data coming from these edge nodes. So that's the N in the beginning, node data, node command. And then we have also birth and death of devices. So these message types starting with D stand for device, birth and death, and data and command. And then we also have a state message type for our host, for our primary application. Yeah, and we have another layer, the edge node ID and the device ID, to structure our topic namespace. Let's look at the payload of Sparkplug-B over MQTT. Sparkplug-B uses and relies on Google protocol buffers. And what Google protocol buffers are, we will also see in a minute. Here you can see some traffic that I captured using Wireshark, some Sparkplug traffic here. And as you can see, you cannot see much without interpretation of this Sparkplug payload. So it's a binary encoding, which you have to decode, of course, to understand what's inside of this payload. Excuse me for 1 second, just have to cough real quick. And I'm back. Okay, so protobuf has been invented by Google, and yeah, is a way to deserialize structured data to and from a compact forward and backward compatible binary format. And the general approach is that you have a definition, a so-called proto definition. The Sparkplug-B proto definition is one main part that is specified by the Sparkplug working group. And then you have a compiler, this proto-C in the middle, and you can automatically generate source code for different programming languages according to this proto definition. Yeah, and then to this payload definition, you add the state management part of Sparkplug-B, and you add the topic namespace part of Sparkplug-B, and what you get is a so-called Eclipse Tahoe project, which is the reference implementation of Sparkplug-B. You can also find on the Eclipse website. And the approach now is that you use this, for instance, Tahoe implementation, and then you have, of course, proto buffer serialization and deserialization in your apps that use these client libraries, and the Sparkplug app 1 on the top can then, for instance, serialize data that's published to a message broker binary format, and the Sparkplug app 2 can deserialize it and understand it. And if we look at the same Ethernet frame captured in Wireshark that we saw before with enabled Sparkplug dissector in our Wireshark, then we can see that we can now decode the Sparkplug payload. And we, for instance, see down in this picture the protocol buffers with the different fields like a timestamp and metrics that we can now decode. Okay, but what's the payload in Sparkplug? Maybe let's look at that for a minute. And on the right, you can see a JSON-like representation, but it's just to make it human readable, since we just saw that it's not human readable. It's a binary format. You cannot directly read it, but yeah, JSON is always nice to understand data structures. So here on the slide are some examples for metrics, for instance, which are in the end, an array of type node or device metrics as a key value and data type, and also additional metadata that can be contained to describe these metrics. So metadata can be in explaining strings, some plain text, or JSON or XML file. And you can also add some properties to your metrics, for instance, SI units and so on. So then going on, there are also some user-defined types, they are called in Sparkplug-B, and this is the object-oriented approach to model complex types in Sparkplug. And these object-oriented modeled complex types are defined by the user. That's why they are called user-defined types, of course. And these types are then published to the broker, and that's what you might also hear, this edge-driven philosophy. So you define your UDTs on the edge and publish them to the broker in this edge-driven approach. These UDTs also have parameters, which basically means a field that's common across such a UDT template definition. But the values are unique to template instances. So you have, for instance, here in the example, a drive type, and then you have a parameter drive number, and it would be then incremented for the template instances of this UDT. Okay, let's look at the state management in Sparkplug-B, coming back to our architecture that we already saw. State management, as we said before, is about the online or offline status of our devices and our edge nodes. And there, these birth and death certificates are used. So if a Sparkplug enabled device connects to this MQTT network, it announces available metrics, for instance, in this birth certificate, allowing other devices and applications to be aware of what is coming, which data is being published. And this death message signals the device going offline. And this also is based on a last will functionality of MQTT, which is sort of like a testament. So when a device goes offline or a node goes offline, the MQTT broker sets the status to offline and the values to stale, and the primary application, for instance, knows that these values are not updated anymore because the application, the node or the device is offline. Okay, so far an overview about Sparkplug-B. So we are going over to OPC UA over MQTT now, and there we have another poll question for you. So wake up and Matt, please launch the poll. The question is, which communication model does OPC UA support? What do you think? Client server or publish subscribe? Okay, let's look at the results. So 26% client server, 10% publish subscribe, 63% both. Excellent. Okay, so both is correct, of course, as we will also see in our presentation now. So what is OPC UA? OPC Unified Architecture is an industrial interoperability framework. It's not a protocol, and it's an IEC standard 62541 that is developed by the so-called OPC UA Foundation, consisting of over 980 members. OPC UA can be understood just like a toolbox for Industry 4.0 communication that we can see on the right of this slide here. So we have different modules, different tools in our toolbox, for instance, starting on the left, different transport methods, different transport paradigms, like client server and pub/sub we just had in the poll. Then we have cybersecurity aspects. We have specified information access services and base models. And then we have a very important part of our OPC UA toolbox, which is the information modeling part that we will also see in a minute. OPC UA offers end-to-end cybersecurity, also for OPC UA over MQTT, as we will see, and is recently certified by the German Federal Office for Information Security. OPC UA offers a compliance and certification program, conformance testing, based on a lot of test scripts for OPC UA, and also OPC UA's companion specifications. What that is, we will also see in a minute. OPC UA includes these standardized information models for Industry 4.0, these companion specifications, and today over 153 companion specifications are available on the public website. We already saw that it supports client server and pub/sub, and most of you also know this, and also discovery mechanisms are included in OPC UA. So both communication models, as we saw, are supported, client server and pub/sub. So not much to add here. If we look at the device 2 OPC UA server at the bottom here, our OPC UA application, we have an information model, and we select parts of this information model as a so-called data set that the data set writer then publishes to our message-oriented infrastructure. Where, for instance, in this example, device 3 and device 4 subscribe to these values for instance, our condition monitoring application. And in parallel, we can also have client-server connections based on a request-response pattern. Here in this example, device 1 connects to device 2 via client-server. OPC UA has a very full-featured transport protocol stack. If you look at the OSI layered model here, we have the basic client-server model on the right. We do not have to talk about this now. And we have two different OPC UA pub/sub approaches for our message-oriented infrastructure. Starting on the left, we have a brokerless variant where we use the network to publish our data in multicast messages via UDP, for instance, on the transport layer. And there's also a direct Ethernet mapping, especially for real-time communication use cases. And let me highlight some points regarding OPC UA pub/sub in general. So on the top of this figure here, you see a configuration tool. And that is a very important point for OPC UA, which comprises a configuration model where you can configure your publishers and subscribers, for instance, just via general OPC UA clients. So you can connect with an OPC UA client to a server that is also a publisher and configure via this configuration model contained in the server which parts of this server should be published and with which cycle time and so on. And of course, this configuration tool does not have to be an OPC UA client, or this OPC UA client can be contained in some engineering tool. But the point here is you have a configuration tool and a configuration model in the first place. And you have metadata that is exchanged independent of the general data messages that describes the data messages. And you have this mechanism to distribute keys for cyber security aspects. So let's look a little bit closer at OPC UA over MQTT. So as we just saw, it's just one subset of our OPC UA transport toolbox. For instance, you can also do pub/sub broker-based via MQP, but of course today the focus is on MQTT. And if you look at this orange part of the figure here that's highlighted, you see that we have two message mappings, UADP, also a binary encoding, and also a human readable JSON message mapping, which has some advantages. If you can directly look at the broker, if you remember our example also from Wireshark before, where we could not read without having the Sparkplug protobuf deserialization mechanism in place. This JSON is of course always readable also on the broker directly. OPC UA supports a standardized topic tree in the latest version of the PubSub specification, specifically for discovery, status, and semantic information. Also, there's a suggestion for data, but it's not mandatory. So you can have your own topic tree in OPC UA over MQTT for your data messages. UADP binary encoding allows end-to-end security. So, for instance, the broker in this use case is then not able to read your message. So the broker is, of course, a man in the middle. And most of the time it can read the data and sometimes also has to read the data from the publishers to distribute it to the right places. But with OPC UA's UADP encoding, you can, if you want, ensure end-to-end security so that also the broker is not able to read your messages. And OPC UA over MQTT is supported by AWS and Microsoft Azure clouds. Let's look at OPC UA over MQTT's topic tree. It starts with a prefix. It's also not mandatory, but the default value is OPC UA here. Then you have an encoding that is JSON or UADP, as we just discussed. And you have also different message types for data, metadata, and some more. Here, you have a publisher ID that uniquely identifies the publisher within the scope of your defined prefix, and also writer group and dataset writer to structure this topic namespace further. So quite similar. Let's look at some examples for this topic tree. So for instance, you could subscribe to the status of devices with the first topic that we see here. You can subscribe to all the data from a device 1 here in the second line, or you can subscribe to all diagnostic data that's available, or diagnostic writers that are available in a topic namespace. And you can, of course, also subscribe to metadata. And we see a payload example for describing metadata at the bottom of this slide. And I just want to highlight the green part. So you can imagine that it's, for instance, a data field with the name temperature, and you get some metadata here. The data type, the unit is degrees Celsius, and you have the normal range of 1 to 100 that is specified here in this metadata message. OPC UA information models are very important, as I said before, and this is OPC UA's object-oriented approach for modeling complex objects. It's an object-oriented information model, so basically consisting of a network of nodes and relationships between these nodes. These nodes can be variables, methods, and events, and you can create arbitrary hierarchies. A main point is also that you have a type and instance space, always also already in an OPC UA server. And what this means is that you can not only browse the instance space, but also always the type space as a client. So you can understand types on the fly without having to know them in advance. That's the basically what it means. For instance, on the right, we see an example from our guideline with the VDMA for a machine tool information model. And such an information model can be standardized and contain all universally applicable variables, state machines, or events of a machine tool. And that's the whole idea, right? Standardizing such information models, not inventing the wheel over and over again, using the same information models and the same information information model parts or elements for different devices and, of course, machines of different vendors. So in the end, the goal is, of course, on the left, you have machine tools using already a uniform communication interface, but different information models. You see an information model A and B. And the systems, for instance, our SCADA system has to understand both, of course, if you want to interpret the data from both of these machines. And standardization, of course, then means that the two machine tools speak the same information model, use the same information model that is standardized across these machine tools. And this is the approach for the OPC UA companion specifications. And there's a lot going on also here in Germany in the VDMA. In total, the OPC Foundation and different partners have already standardized over 153 companion specs that are available on the public website. And in the German VDMA alone, 69 companion specs are available for different domains. You can see some examples on the bottom of this slide. Yeah, and before we now come to our requirements analysis, let me highlight how to also communicate OPC UA information models over MQTT. You see a picture from the beginning here, and our information model from which we publish parts, right, to our message-oriented infrastructure. So we select data to be published and also metadata describing this data. Yeah, to the best of our knowledge, we then think what a subscribing application might need as metadata to interpret it. But of course, we do not publish the whole information model, the whole standardized information model periodically, especially to our message-oriented infrastructure. So there are some mechanisms in place to resolve missing links, so to say, of our object-oriented information model by either having the companion specification pre-configured in our server, or there's also the UA cloud library, which we can connect to via REST API, and where we can query missing links in our address space, OPC UA address space. Okay, so looking at the time, let's come to our requirements analysis. So we had some requirements derived in the beginning and looked at different solutions, Sparkplug and OPC UA over MQTT, and now let's see how they compare here according to these requirements. So both the solutions address a uniform communication interface. OPC over MQTT standardizes the topic tree, especially for discovery status, metadata, and data, which is optional. So you can also have custom topic structures for your data. We have a UADP binary encoding and a human readable JSON encoding in OPC UA. In Sparkplug B, we have a fixed topic namespace and we have protobuf as a binary encoding. Standardized semantic information models, we have over 153 companion specs in OPC UA and no standardized semantic information model in Sparkplug B. And now the third requirement, scalability. Let me just quote here. While the basic notion is intuitive, scalability has no generally accepted definition. For this reason, current use of the term adds more to marketing potential than technical insight. I think this is a really good quote because, scalability is like digital twin, right? You always have to define what you mean when you talk to people. Everybody understands it a little bit differently. So here we understand that scalability is the property of a system to handle a growing amount of work. A system that does not scale well adds to labor costs or harms the quality of service. So I would here also like to differentiate between load scalability, which means the ability for a distributed system to expand and contract to accommodate heavier or lighter loads, and functional scalability, which is the ability to enhance the system by adding new functionality without disrupting existing activities. So coming to functional scalability, in OPC UA over MQTT or PubSub in general, we have this configuration model. We have topics that publish semantic information from companion specs, or where we publish this information to. And coming to the workload, we of course have a scalable MQTT-based architecture in general, and we have different implementation profiles that we can implement from sensor to cloud, and there are various SDKs available for OPC UA in multiplicity of programming languages. Sparkplug B, you have your configuration in source code or specific tools. You have the user-defined types and this edge-driven philosophy, right? You define your types at the edge and push them to the broker. It's more like an agile approach here, not so much a top-down approach. And when it comes to the workload, we also have a scalable MQTT architecture and Eclipse Tahoe implementations. The next requirement is the low bandwidth, and there we are currently conducting some experiments where we have a specified information model. Then we have an OPC UA publisher and a Sparkplug B publisher. We acquire these messages with Wireshark and analyze the size of the MQTT payload. This is an ongoing experiment that we will publish in the paper later this year. And I would just like to highlight some first results that we saw here. So we compare to the OPC UA JSON human readable format, which is the biggest encoding, of course, and UADP. There we have a ratio of 2, so OPC UA JSON is twice the size of the UADP encoded payload. And if we look at protobuf, the OPC UA JSON is 18 times the protobuf encoding. So the protobuf encoding is quite efficient here for this requirement. Cybersecurity, in OPC UA, we have the TLS and MQTT basic security. We have application-to-application integrity and confidentiality for the UADP decoding, encoding, and non-repudiation for the JSON encoding. And we have a review by our BSI in Germany. In Sparkplug B, we have the basic TLS and MQTT security features. Both are international standard. 981 members in the OPC Foundation are adopting OPC UA in general, and there's an MQTT activity going on, the Plugfest, especially with over 51 companies from OT and also AWS and Microsoft Azure that are participating in these OPC UA over MQTT activities. For Sparkplug B, we have 12 companies listed on the Sparkplug public website. Compliance and certification. For OPC UA, there's a conformance test tool with 1,800 test scripts for the core OPC UA specification and also the companion specs. And there's the optional certification that's possible in the third-party test lab. For Sparkplug B, there's a technology compatibility kit where we can certify our host application, edge nodes, and MQTT brokers. So let me conclude. Efficient implementation of Industry 4.0 requires, from my point of view, standardized information models. And while more of these information models exist, challenges arise regarding their scalable communication. And for this, MQTT achieves increasing attention in IIoT use cases, but let alone might be a step back because it's data agnostic. The payload is not specified. Sparkplug B specifies a fixed topic namespace and efficient protobuf payload definition. Following an edge-driven philosophy, metadata and data to be published are defined by the user. OPC UA is an established standard supporting multiple communication models, message encodings, transport mappings, end-to-end security, and can be configured via configuration model without having to change any source code. And OPC UA has a strong focus on semantic information modeling. Sparkplug B, in my conclusion, can be a good choice for the implementation of condition monitoring, especially if bandwidth is a priority and the manual effort for data modeling and coding is not. OPC UA fulfills all the requirements of plug-and-work and condition monitoring application scenarios, especially because of its semantic information modeling capabilities. And with that said, I would like to conclude end my talk and hand over to Jack again for maybe at least 1 or 2 questions. Thanks.
Thank you, Florian, for that excellent presentation. And we have time for a few questions. And as a reminder, use the questions tab on your screen to submit your questions. And we'll get to as many as we can. Those we don't get to will be responded to by email. Hey, Florian, let's get started. Does OPC UA support report by exception?
Oh, that's an excellent question. So yes, that's the answer. So Sparkplug B, of course, supports report by exception. It also calls it report by exception. And in OPC UA, there's a feature called delta frames. And these delta frames also only report by exception and also only include data changes that are then published. Yeah.
Okay, thanks. That was a good answer. Next question. In the beginning, you said that in order to create added value in Industry 4.0, international standardization is the key because information has to be exchanged between value chain partners. But is this true for the scenarios you showed, such as condition monitoring?
Oh yeah, also a good question. So yeah, most of the time condition monitoring, you think of a one component, one machine, or one company, but condition monitoring can be better collaboratively. So we have also a scenario that we call collaborative condition monitoring, where multiple vendors work together, put their data together. Also, of course, across the value chain of our production system. And the hypothesis here is that condition monitoring gets much better, gets much more accurate results if the different vendors work together, put their data together via standardized semantic information models, of course.
Is it a good practice to use Sparkplug B format to store even in the historian?
Well, that's also a good question. I don't see any reason why not to. So of course you have to, you need a Sparkplug capable application, deserializing especially the protobuf encoded payload with your metrics inside, and these you can also then of course write into the historian. But if the question is storing the protobuf encoded payload, then the answer would of course be no. So decode it and then put it into the historian.
Okay, the next question might be kind of a loaded question and maybe a long answer. What standards exist for Industry 4.0?
Okay, so as I said in the beginning, the VDMA, for instance, promotes OPC UA for Industry 4.0 communication, especially in the operational phase of an asset or a machine. And if it comes across to communication across the whole life cycle of such a machine, so which then also starts already in the development phase, the engineering phase of such a machine, where you have some other data, right, like CAD plans and IEC 61131 programs and so on. Then we have another standard that we are working on in Platform Industry 4.0 since many, many years, which is called the Asset Administration Shell, which is sort of the standardized interoperable digital twin for Industry 4.0. And we use this format especially to exchange data across the whole life cycle, which is another dimension here.
What else was considered as an alternative to MQTT, if anything?
Well, in OPC UA, PubSub, you, for instance, also have another broker-based approach, which is MQP, which stems more out of the financial sector and is not so popular for IoT scenarios. I hope I got the question right.
If a device or a node goes offline in a catastrophic way, like for example, a power failure, or disconnects from the network, how does that typically get reported to the application?
Yeah, well, there's this last will statement in MQTT. So basically the broker recognizes that the device went offline, and then there's a sort of like a testament, the last will statement, right? So what the device wants the data to be, and what the device wants to say or tell other consuming parties if it dies, right? So that's the methodology behind this.
Do you see batch information represented in native MQTT and Sparkplug B?
Oh, okay. I cannot answer that question right now. I will have a look and answer this question via email later.
Fair enough. What is the recommended strategy to implement UNS as per ISA 95 and S88 physical model using OPC UA PubSub over MQTT? I can read that again if you want.
Yeah, go ahead.
Now, what is the recommended strategy for implementing UNS according to ISA 95/S88 physical model using OPC UA pub/sub over MQTT?
Okay, yeah, so UNS is a unified namespace that is talked about a lot these days, and this basically means that yeah, you publish everything into your MQTT broker, right? It's maybe a basic architectural approach to create a digital twin of your machine or asset in general in the MQTT broker, in the MQTT world. And yeah, you can also implement this concept with OPC UA over MQTT. We saw the topic tree before. So yeah, there are some approaches and also prototypes already available from the OPC Foundation. So there's a guy called Randy Armstrong active in this field. And there are some open source examples that you could also have a look at. Maybe just search for IIoT or UAIIoT starter kit on the OPC Foundation GitHub. That would be my suggestion. There are 4 really nice and easy to follow quick starts. And yeah, just have a look at those, and you will find out how to implement your UNS with OPC UA. And by the way, we are also working in that direction and implementing a prototype here in our Smart Factory OWL. So if you're interested in that, then yeah, just get in contact, get in touch, and we can talk about the details.
What is the level of adoption of OPC UA outside of Germany?
That's a question for the OPC Foundation, but OPC is really a well-established international standard. That's what I would say. So there are a lot of events going on also in the US and also in Asia. So my feeling would be that it's well adopted, really. But yeah, I'm pretty sure you can find some figures about that on the OPC Foundation website. Maybe just look at the members on the website and the regions they are coming from. Right.
So it looks like we're just about out of time. Florian, would you like to make any closing remarks on this?
Yeah, thanks for the opportunity today to talk to you all. Thanks automation.com. It was a pleasure, and I hope I could share some insights about Sparkplug and OPC UA and MQTT in general for Industry 4.0. If you're interested in the topic, yeah, get in contact. It would be really a pleasure also to work together on this topic, for instance, to prototype the UNS with OPC UA over MQTT and also Sparkplug, and yeah, share our results. That would be great. Thanks.
I want to thank Florian Pethig for being here today and sharing his outstanding information. And I'd like to thank all of you for attending. I also want to remind you that if you missed any portion of this webinar, or you would like to listen to it again, the presentation and the question session will be available on demand. Within the next 24 hours, you will receive an email with a link to the recording. You will also receive a post-webinar survey. Please take a moment to respond to it so we can continue to improve your experience. On behalf of automation.com and Fraunhofer, I want to thank you for your attention. This concludes our presentation.